Okay, E1 elimination. Okay, E1 elimination, if you remember SN1, there are many occasions it can be the leaving group produce carbocation, or protonation, protonation of the alcohol first, and then remove water, give a carbocation. There are two ways we did in SN1. We'll see very similar in the E1. Okay. And so E1 is the same, the two-step leaving group, carbocation. The carbocation, instead of have a nucleophile to attack, here's actually use a base to take away the protons. That's the big difference between the E1 and SN1. Is a base take away the beta proton, form double bond. And again, the leaving group leaving is the rate determining. The carbocations, as we did before, similar stabilities. Tertiary is the most easiest to form the carbocation. And the reason because very similar, the tertiaries, carbocation is very stable. Carbocation is an intermediate carbocation here. It's more stable, so you have a less activation energy. Okay, and then the difference in the second step, SN1 is nucleophile to combine, to react with the carbocation. Then E1 is the base. Instead of attacking the carbocation, it attacked the hydrogen, take away the hydrogen. So that's the difference between these two. And this chapter, getting confusing part, it is how do you know when you have all these reagents, substrate? What kind of reaction? Now we have four directions. SN1, SN2, E1, E2, there are four directions. Which way to go? And so that's the difference. Depends on the base react or the nucleophile react. By the way, the many nucleophiles are base. And not all of them, but many nucleophiles are base. And so that's the interesting part. We have a table to compare. We need to remember quite a few. Which are the better base? Which one's a better nucleophile? And so that's where the E1 elimination, if you start from halides, is simply just the halide eliminate as a leaving group, form the carbocations. But when we have an alcohol, and you can see some of the reaction, from alcohol form the alkene, the double bond, it is through the, again, alcohol is not a good leaving group. It cannot leave by itself, form carbocations. It will not go that direction. So therefore, just like the SN1, it first step start with the protonation. And the protonation give the proton to the OH group, which is a weak base, and the protonated alcohol. Now you have water as a leaving group. It's much better. And water leaving group left form the carbocation. Oftentimes, the protonation, of course, we're talking about use a strong acid to give proton to the alcohol. And the strong acid, we have quite a few options. Concentrated sulfuric acid is one of the good acid, very suitable, because it not only protonated the OH group in the alcohol, because it's strong acid, and also the concentrated sulfuric acid, it absorbs moisture like crazy. It really take water from anything, even come from the cotton fiber. The sulfuric acid dehydrate even the cotton fiber, even burn a hole on the jeans. This is a very known fact among the chemists. It can burn the hole on the blue jeans, cotton fiber. Because the concentrated sulfuric acid also, it take away the water from the system. So according to Le Chatelier's principle, it helped the equilibrium shift to the right to form the alkene. And this reaction, by the way, is entropy increase. So therefore, high temperature really helps. And so that's the, when you have a tertiary alcohol and use a concentrated acid, high temperature, it give you mainly the more substituted alkene. And this is very similar to what we've seen before, the Zaitsev elimination. Give the alkene has more substituent, the Zaitsev product. And so the very last step is remove the protons. Okay. This is the reaction when you have a secondary alcohol. The secondary alcohol also been protonated by the strong acid, and the water as a leaving group give a carbocation. And then we, from the carbocation to form the alkene, well, there's two hydrogens can be eliminated by after the forming carbocation. As we find from the experiment, the major product is the trans. It's just like the we've seen before. When you have a losing the either two hydrogen to give you either cis and trans product. Trans product is normally the trans isomers or E isomers are the main product because they are more stable thermodynamically. Okay, so E1 reactions. Let's say we have this reaction treated with concentrated sulfuric acid. What is the main product? So once we remove the OH, form a carbocation, let's see how many hydrogens, how many beta hydrogen we have. Okay, so this is the alpha carbon. We have beta carbon here. This is another beta. And here another beta. So these are the beta carbons we have. And which carbon have hydrogens? So let's see, this one has 3 hydrogens. Very good, this has 3 hydrogens. This carbon has 1 hydrogen, okay. This beta have 2 hydrogens. So that means I can have a whole bunch of possibilities to lose, to form the alkene. I could have formed this, or this, or this. Basically, these 3 are the bond that I can form double bond. So according to what we learned the pattern before, it has to be the Zaitsev product, and if there is cis and trans, E or Z, it goes to the E is preferred. So that's basically, we can write a, let me see, 2 here, 2, 1, 2, 2. We could have 4 different alkenes can form from this product, because when you lose this, you get only 1 product. So 4 or 5 different alkenes I can get, all possible possibilities. So remember what we learned is the most substituted alkene is most stable. So we need to draw out all the possibilities. Let's start from this. Okay, start from this, and let's see what we get. You copy most of the structures, and you lose this hydrogen. I get this alkene. This is my first product, and the second one. Second, let's go this. Okay, let's go here. When you form double bond here, we have boom, boom, boom. No longer wedge and dash, because now becomes a coplanar carbon. And this is a methyl group. This is this. This is the losing the hydrogen, this hydrogen, and form double bond here. Double bond here. Okay, remember I can form isomers by rotating this. So rotating this, I get different structures. I keep the same and switch these 2. So this is also a possibility. So between these two are the isomers, E and Z isomers. And finally get to this one. This one, I can have, again, two possibilities. And so that becomes a methyl group. I get a wedged methyl group here. And I'm forming, this is double bond. All right, so this is double bond. This is one of the product. One of the product. The other ones, if I rotate this, I get the isomers. All right, so I get 5 different molecules. Okay, 5 different molecules. We're supposed to get a 6, but this carbon have 3 hydrogens. You get no difference. So therefore, I get only 1. There's no isomers by rotating this double bond. So we got all 5 possibilities. By the way, this is take some time to really develop. It really take some practice, get into the can come up with different possibilities so quickly. Anyway, and so what are the what is the most stable? The alkene group need to have the most substituent. So let's switch to different colors. Okay. If you look at this alkyl group, you got only 2 alkyl groups substituted. This is not good. It's not stable. Okay. Have only 2 alkyl groups substituent on the alkene. And if you look at this, how many alkene group on this? How many substituent, carbon substituent on this alkene? How about you guys tell me? How many alkyl groups on this alkene? Can you guys see that? How many? That should be hydrogen. How many alkyl groups on this alkene? 2, 3, 4, up to 4. How many? Anyone? Only 3, right, you guys? Only 3 alkyl group. And so it's better than 2. Okay, both are 3 alkyl group. Finally, this is good. All 4 positions on the double bond are with a alkyl group. So this is the most stable. These 2 are the better ones. And between these 2, the difference is this bulky group is on the cross 180 degrees from the double bond. This is the E isomer because the bulky group against each other across the double bond. Whereas this, the bulky group on the same side of the double bond. This is the Z Z isomer. Between these 2, this is preferred. So final answer, this is the alkene, should be the main product. And so this example takes some time to develop, and it's good practice. So you go home to kind of redo this example and find out all the possibilities. So the mechanism, the arrow pushing. The arrow pushing for the E1 mechanism is very similar. It shares similar steps as SN1. The first step is very similar. Is the end different? The SN1 is nucleophilic attack. Elimination is the base attack. Base take away the protons, proton transfer. And so that's the difference. So the following, I write down some reaction mechanisms. And so it depends on what is the substrate, what is the initial reactant. It goes through different pathways. But in general, we'll never see the alcohol go through elimination and become alkene. it need to be protonated first and form a carbocation, and then base attack, form a double bond. So there it is. It's a very classic, simple mechanism for alcohol losing the water become alkene. And with concentrated sulfuric acid, the first step is protonation. With acid, the acid give the hydrogen, and it is the alcohol attack. And the acid is sulfuric acid. Sulfuric acid, write down Lewis structure. You got a 2 double bond with oxygen. So that's the first step. It formed a bisulfate or hydrogen sulfate ion, and the alcohol becomes a protonated. Basically keep all the structures the same, and only the oxygen attach more protons. Okay, and also the alcohol gain a positive charge. This reaction, the product, there's not a product, it's a bisulfate. Normally we don't write the full Lewis structure for bisulfate. But just put it down here. Normally we normally don't care about the inorganic product, only focus on the organic product. And so this is E1 reaction. The second step, form the carbocations. One step, leaving group left. I'll give you the carbocation. Now the carbocation lose the water, become trigonoplanar. Is the carbocation with 3 methyl groups. They're fairly stable because the hyperconjugation effect. And so last step is elimination. There's quite a few hydrogens here. And as a base, the base, okay, what is base? In this system, you have a sulfuric acid. This cannot be the base. Actually, it turned out to have bisulfate be the base. Bisulfate is, by the way, it's a very strong acid, so it's not so good base, but that's the only base we have. So the base take away the proton. Base will take away the proton. And there's another base, by the way. There's another base, because this reaction, once you form the carbocation, you form the water. Water is a much better base than the bisulfate. It should be bisulfate. Okay, let me see. Yeah, so either the bisulfate or the water as conjugate base. Oh no, this part I don't remember. Let me see. Let me see what the book says. Yeah, this reaction mechanism, when you have a strong acid, strong base, the mechanism keeps getting complicated. Let's see what they say about chapter 7, elimination with alcohol. You got a water as a base or bisulfate as base. Both has pros and cons. The water is supposed to be a stronger base than bisulfate because when they form the, yeah, so it all depends on which one's stronger base. So let me think about this without checking my book. This gain the proton become hydronium. Okay. That's conjugate acid. And this gain the proton becomes sulfuric acid. Which acid is stronger? By deciding which acid is stronger, then I can know which one is the stronger base. Hydronium, sulfuric acid. I think this is stronger acid. The stronger acid than the hydronium. Because as I remember, the sulfuric acid put in water, there's a leveling effect. And sulfuric acid become weaker acid by losing proton form hydroniums. So anyway, this is stronger acid. Therefore, the base must be a weaker base. So this is actually a weaker base than water. Okay. As an acid, this is stronger than hydronium. Therefore, as a base, bisulfate and the water, this is a better, stronger base. Okay, are you guys following my logic? So my conclusion is it must be the base take away the proton. This is kind of strange because we are dealing with a concentrated sulfuric acid. The solution is highly, extremely acidic. How come there's base? Well, according to the Bronsted-Lowry theory, anything can be a base. Anything, any atom, as long as they have a lone pair, it can be base. So the idea is, based on the analysis, it has to be the water, act like base. The water then take away the protons, one of the protons, and this bond break form double bond, leave the electrons. The positive charge become neutralized and form a double bond. Give you the final product. So that's when you have a strong acid elimination. If you summarize, first step of protonation, and then losing water, leaving group leaving from carbocations. Carbocation need a base to lose the proton 2 from alkene. So basically that's what happened. So in the quiz exam, you're supposed to know how to write those the mechanisms, error pushing, just like we see before. By the time we take a midterm, you will not be seeing the questions asking about those 5 error pushings. Instead, it will be question asked about the write down the errors for the SN1, SN2, especially SN1 and E1 mechanisms. Okay. And this is the E1 mechanism. No rearrangement, simplest. But we had those situations decided what is the base to make this reaction happen. You can see the base, the base actually to take away protons, it is a product in the second step. When you form the carbocations, you are forming water. By the way, water is one of the final product. And you can see the water is kind of a catalyst because even though it's a final product, it helps take away the proton, act like a base. So water, even though it's a very extremely weak base, it does do the job to take the protons. Okay, next example with a rearrangement. How come there's a rearrangement? You can see there's a carbon have a 3 methyl group attached. And this carbon have only 1 methyl group. And it looks at product. This carbon to the left, it loses 1 methyl group. And whereas this carbon, the right-hand carbon, after losing the OH, it gained the 1 methyl group. So you can see that's basically rearrangement taking place. The rearrangement taking place, that means you have one more step than the what we see in the last slide. And so this will be very similar as the last one. First step, protonation. You have the just take the proton from sulfuric acid, and the product is first step, protonation. And then the water as a leaving group. Water as a leaving group. I'm sorry. Water. The arrow should point to the oxygen. Okay. And we have a carbocation. Okay. Okay. And now you can see the carbocation next to a quaternary carbon. when carbocation next to a quaternary, methyl shift, not hydride shift, methyl shift. So next step is simply the methyl group with 2 electrons migrate to the carbocation. Now you have no more carbocation because methyl group with electrons come in. Instead, carbocation, it'll be end up where the methyl group used to be. Okay. And then look at the final product. Even though we have multiple beta hydrogens available, it is this to be eliminated, not this one. Okay, not this one. So this need to be gone. Gone. Again, we use the base, and for the base we have a bisulfate ion, water. Water is better; it's a stronger base. So water to take away the hydrogen. And oh, I need to undo this. Okay. And this hydrogen, this bond, forms double bond here. Lone pair start, the arrow start from lone pair. And then we get the final product. So we have one more step. This is the rearrangement step, methyl shift. There's more rearrangement. It's very similar as we've seen before, but this, the difference is we start from the halide. That means we don't need a protonation to make loose halides. This is actually simpler without protonation. Okay, so the first step is simply just chloride leaves give you carbocation. Okay, and then if you look at the product, before we do the arrow pushing, we need to kind of analyze the structure, see what is happening with the structure. The biggest difference, you can see this carbon, central carbon, now has only one methyl group. You can see there's a big change in the carbon backbone. It must come from the rearrangement. And come from rearrangement, it cannot be the SN1 or E1. I'm sorry, the SN2 or E2. It has to be the SN1, E1, where the carbocation is involved. So the carbocation, that's why the first step, it is the form of the carbocation. And then based on the structure, you can see this is where it's from. This is where the end is. The end is showing this middle carbon have one less methyl group. The methyl group in the middle must be shifted. Shifted here. Okay. Move to methyl group, shift to here. And after that shift, we have this have quite a few steps. And this carbon gain one methyl group. The middle carbon, the number 3 carbon, it lose one methyl. Now have only one methyl. And not only lose one carbon, it gained one positive charge. Methyl group, methyl shift, hydride shift, it means the hydrogen or methyl group moved, and also charge changed location. And then, okay, so getting to the very end. The next step, the carbocation can either combine with water, become alcohol, or go through elimination. And the elimination looks like this carbon lose the hydrogen. It must be this carbon. By the way, when you get into this carbocation, you get two groups, the two isopropyl groups. Each one have one hydrogen, beta hydrogen. So reaction can go either ways. It doesn't matter. So whichever hydrogen lost, you get the same product. So to lose the hydrogen, we need a base. What is the base we have in this condition? So if you look at the beginning, we lost one of the product is chloride ion. And if water also can be a base. Chloride can be a base. Which one is stronger base? Again, you think about the conjugate acid. Hydronium, HCl, these are the conjugate acids for these two. The stronger acid, like the HCl is stronger acid. This is stronger acid. Because HCl reacts with water, give all the proton to water. So that's a proof. Water is stronger base. This is stronger acid. Therefore, the chloride must be a weaker base, which means water is a stronger base. And so the last step is water take away the proton. And water take away the base and give you the alkene. So the reaction mechanism with the eliminating agent with the base, it gives you the alkene. And there's quite a few different pathways. Rearrangement is one of the more difficult, need more thinking. Okay, any questions? I think so far this material is quite a bit overwhelming to take some time to absorb. This is the easy part. Okay, reaction energy diagrams. You're not required to memorize those derivative peaks. It just shows you every value has an intermediate, and you have a 1, 2, 3, 4 transition states, which means 4 steps. We have 4 steps. So not big deal. And this thermodynamically, the alkene is more stable than alcohol, and that's pretty much all the information we have. Don't worry about those. This is the practice, draw reaction mechanisms. By the way, when you look at the alcohol and the alkene, and you notice this carbon backbone change. The carbon has changed from the 5 carbon ring to a 6 carbon ring. What does this mean? Is it the rearrangement involved? Anyone can help me think?
Yes.
Yes, there must be a rearrangement. So if the rearrangement involved, would that be the E2 or E1? E2 will no carbocation. E1 says carbocation.
So E1.
So it must be the E1 to form the carbocation. And that's basically the very similar as we did before. But now we just you have the same protonation, and then dehydrate from carbocations as a second step. That would be the first step. And so this is basically it's similar to what we did before. You add the, I'm kind of lazy. I just write down sulfuric acid just like this, without the bonding sulfuric acid, and give you the carbocation. And this water left, give you the carbocation. Now finally we're getting to the carbocation. And again, carbocation, this is secondary, not stable. Next to a tertiary carbon. When you're next to a tertiary carbon, you can either have the hydride shift, or this whole alkyl group, this whole carbon, this carbon move Which one is taking place? Is hydride or the carbon move?
The carbon move.
Why not hydride? Well, normally it should be hydride, but here, if you look at our product, it's not a hydride move. If hydride, wait a minute. Let me think about it. What's happening here? I think this both will work, by the way. Would that? No. If hydride move here, the carbocation will be here. We will not get the final product. So it cannot be the hydride move. You guys following? Because if hydride move, carbocation will be here, tertiary, and then we just lose a proton to form the a alkene that has 5 carbon in the ring. This cannot be that. So it must be this alkyl group move. So by the way, the same thinking when you discuss, like you saw the last question in Zapling, and you have one reactant and give you 2 products. What is this reactant? You have to think kind of this way. You try it. If that is the reactant, what would happen? If the other be the reactant, what would happen? It's just like this. Or anyway, so this carbon move, that means you're going to break this bond, and this bond will form here. Bond form here. Now the ring, it is a 6 carbon ring. By the way, it looks kind of strange, but so I need to keep that as the same as much as possible. So that way, give our brain a little time to transit. We're getting this next step. Are you guys following? This carbon, instead of bonding this, it bonding with that. And also, I put it wrong place, by the way. The carbocation is not in the right place. Because every time the methyl group moved, the positive charge changed location. Now the carbocation is here. Make sense? This kind of looks crooked, but this, we can draw the much better looking, prettier cyclohexane. And the carbocation, you can see this carbocation is next to the tertiary carbon. So it's here. Okay, let's put a chart on circle, make it more easy to differentiate from the lines. All right, so we're good. Now we just need to come up with the last step to get to that. It's from the carbocation, lose beta hydrogen. Lose beta hydrogen. With this carbocation, I have 2 hydrogen here to lose, 1 hydrogen here to lose. Which one will give me the final product? Okay, notice our final product, double bond is linked with the carbon has a methyl group. So the double bond has to be here. Make sense? This is kind of, we call it purpose-driven. Reaction mechanism, when you write those steps, it's not simply just to push arrows, push arrows, push arrows. You have to kind of have a goal in your mind. Where am I structure heading to? You have to make your every step, the reaction step, getting closer to your goal. Between this and this, it has to be this one form double bond, which means this hydrogen being removed. Okay, to form double bond here, as in the product, I need to remove this hydrogen. And once we decided which hydrogen to remove, then just pick a base. Again, water is base. Water is, it is the product, but it's a good base. Oh, no. Again, I put an arrow. You can see I did not draw the arrow practice enough. I put the arrows in the wrong place. It happens. Because I did not practice enough. So the arrow should be here to form double bond. And then we're done. Losing the hydrogen, form double bond, we're going to find a product. So we're going to 1, 2, 3, and 4 steps. 4-step mechanism. including rearrangement, and becomes alkene. Alkene. So there's a lot to cover in the reaction mechanisms. Okay, let me pause.